Have you ever been right in the middle of something important on your phone, maybe your computer, and everything's just humming along nicely? And then bam, an app glitches out, software freezes up, or maybe a key feature just stops working.
Oh, yeah. Infuriating.
It's incredibly frustrating, right? And we usually just sigh and, blame the developers. But what if I told you there's this whole army of unseen heroes working away behind the scenes, basically preventing these digital disasters before they even reach you?
The testers.
Exactly. Software testers. Today, we're doing a deep dive into the honestly fascinating world of software testing. We'll explore its core principles, really dig into why it's so critical, and then maybe chart a clearer roadmap towards becoming one of its most vital players. Successful test automation engineer.
It's a great field to get into.
Yeah, and our mission today, let's cut through the jargon, okay? Get straight to the essential stuff, give you a real shortcut to understanding this field. Hopefully plenty of aha moments and maybe some surprising facts from the industry itself.
And it really is critical. I mean,
Yeah.
software just isn't perfect. Bugs, they're unfortunately a reality. And the consequences, they can range from just annoying glitches to, well, catastrophic failures.
Like really serious stuff.
Yeah, we're talking potentially millions of dollars wasted, or sometimes, tragically, even impacting human lives.
Yeah.
Think about Starbucks having to give away free coffee because their registers just stopped working. A software bug.
Wow.
Or the F-35 fighter jet, grounded because its radar software couldn't, detect targets properly. There was even a massive power outage in northern Ohio, lasted 24 hours because a software issue knocked out an alarm system.
No way.
And the most chilling one, back in 1985, Canada's Therac 25 radiation therapy machine. A software bug caused it to deliver lethal doses of radiation. 3 people died, many more were critically injured. These aren't just like isolated incidents. Software failures happen all the time. And that is precisely why software testing is so absolutely paramount.
Gosh, those examples really drive home the point, don't they? It's way beyond just convenience. It's fundamentally about safety, reliability, trust.
Exactly.
So given those stakes, what exactly is software testing then? And who are these people making sure our digital world actually functions? Okay, let's unpack this.
Okay, so at its core, software testing is this systematic process. It's about evaluating software functionality, specifically to find bugs or defects. It's checking if the software meets its specified requirements and, ultimately ensuring we deliver a quality product. Think of it like a two-part thing. Verifying that it works as intended, technically correct.
Right.
And also validating that it meets all the business needs, the technical requirements that actually drove its design in the first place.
So does it work and does it do what we actually need it to do?
Precisely. Does it solve the right problem in the right way?
Okay. And building on that, we have the test automation engineer. Now, this role sounds like it goes beyond just, manually clicking around looking for bugs.
Oh, definitely. Manual testing is important, but it can be slow, repetitive, and honestly prone to human error.
So the automation engineer.
They're the ones designing, building, testing, and deploying effective test automation solutions. They use technology to streamline things, improve the process, automate huge chunks of the testing effort. Basically, an automation engineer handles the planning, the implementation, and the continuous monitoring of that automation tech.
It sounds like the evolution of testing, really, moving from those repetitive manual checks towards smarter, more efficient systems.
That's a good way to put it. It has to evolve with the complexity of software.
Exactly. And for anyone listening now thinking, okay, this sounds interesting, how do I get into this? What's the typical path?
Well, the general roadmap usually starts with a bachelor's degree, often something like software engineering, computer science, or, a related technical field.
Makes sense.
But beyond the degree, you really need to be comfortable collaborating closely with others, developers, product managers, other testers. Teamwork is key. And you need a pretty solid foundation in maths, science, computers, maybe even some electronics, depending on the domain.
So a mix of technical chops and people skills.
Absolutely. You can't automate in the vacuum.
Got it. Now, you mentioned testing isn't just random clicking. It follows key principles.
Yes, definitely. These aren't just vague suggestions. They're like fundamental truths about software quality, and they really guide how we approach testing effectively. There are 7 core ones.
Okay, let's hear them.
First principle, testing shows the presence of defects, not their absence.
Okay. What does that mean exactly?
It means that testing can find bugs that are there, but it can never, ever prove that a product is 100% bug-free. There could always be something lurking you haven't found yet. It's like searching for typos in a huge book. You can find the ones you spot, but you can't swear there isn't another one hidden somewhere.
That's a really crucial distinction, isn't it? It changes the whole goal. It's about reducing risk and boosting confidence, not chasing some impossible idea of perfection.
Exactly. It manages expectations, both for the team and for stakeholders.
Which must be key. Okay, what's principle number 2?
Second, exhaustive testing is impossible.
Impossible.
Pretty much. Think about all the possible combinations of inputs, user actions, environments, data. It's practically infinite for any non-trivial software. So trying to test every single possibility is just impractical. You'd never ship the product.
Right.
Instead, testers have to be smart. They focus on the most significant, highest risk, most impactful test cases, prioritizing based on potential impact and business value.
So strategy over brute force. That makes a lot of sense, especially with how fast development moves today.
Precisely. Which leads nicely into the third principle, early testing. You might hear this called shift left.
Shift left.
Okay. The idea is incredibly simple but powerful. The earlier you find a defect in the whole software development lifecycle, the cheaper and easier it is to fix. Finding a bug in the requirements phase might cost almost nothing to fix. Finding that same bug after the product has been released to customers, that can be incredibly expensive. The cost grows, like, exponentially later on.
Wow. So start testing right away, even when you just have requirements.
As soon as humanly possible. Reviewing requirements, analyzing designs, that's testing too. Find the problems before they even get coded.
But, in the real world, isn't there often massive pressure to just start coding, skip the early checks to hit deadlines? How do you fight that?
That's a constant battle, honestly. It requires a real cultural shift in the organization, getting buy-in from leadership. The argument is that investing that time early prevents much bigger, much more expensive delays and firefighting later. It's seeing testing as woven into development, not just tacked on at the end.
Makes sense. It's an investment, not just a cost. Okay, principle 4.
Fourth is defect clustering. This often aligns with the Pareto principle, the 80-20 rule.
Ah, the 80-20 rule. How does that apply here?
It suggests that roughly 80% of all the software defects tend to be found in about 20% of the system's modules or components.
Interesting. So bugs like to hang out together?
Sort of, yeah. If you find one bug in a particular area of the code, the probability is higher that there might be other related bugs nearby. So it tells testers, if you find a defect, dig deeper in that specific area. Concentrate your efforts where you're already finding issues.
Like finding smoke and then really searching that area for the fire instead of randomly checking the whole building again? Smart.
Exactly. It's about focusing your resources effectively. Number 5 is the pesticide paradox.
Pesticide paradox. Okay, that sounds intriguing.
Yeah, think about it like using the same pesticide on insects over and over. Eventually, the pests develop resistance and the pesticide stops being effective. It's the same with tests. If you run the exact same set of test cases repeatedly, over time, they'll stop finding new bugs. The remaining bugs are resistant to those specific tests.
Huh. So your test suite can actually become less valuable over time if you don't change it.
Precisely. To keep finding new defects, your tests need to be regularly reviewed, updated, revised. You need to write new tests targeting different areas or using different approaches.
That's fascinating. It means testing itself needs to be innovative, not just the software being tested. How do testers actually do that, keep things fresh?
It involves continuous learning, absolutely.
Yeah.
Exploring new test techniques, maybe using different types of data, analyzing where bugs are actually showing up in production, adopting new tools. It's an ongoing cycle of refinement.
Keeps you on your toes. Okay, principle 6.
Sixth, testing is context dependent, meaning the way you test something heavily depends on what kind of application it is, its purpose, its industry, the risks involved. For example, testing a banking application, a fintech product. Security, accuracy, reliability are absolutely paramount. You'd focus heavily there.
Right, you can't afford mistakes with money.
Exactly. But testing, say, a simple mobile game, maybe performance, usability, and just ensuring it's fun are the higher priorities. The testing approach, the depth, the focus, it all changes based on the context.
So you wouldn't test a life support system the same way you test a photo sharing app. The stakes are completely different.
Couldn't said it better myself. The context dictates the strategy.
Okay, and the final principle, number 7.
And finally, number 7, the absence of error fallacy.
Absence of error fallacy.
Okay, this one is subtle but really important. It says that even if you manage to find and fix every single bug, making the system technically 100% error-free, it's still fundamentally useless if it doesn't actually meet the user's needs or solve the intended business problem.
Ah, So you could build the most perfect, bug-free software imaginable, but if nobody actually wants it or can use it to do what they need to do,
It's still a failure. A perfectly coded product that doesn't deliver value is worthless. Testing has to include validating that it meets the requirements and user expectations, not just that the code is clean.
that last one really hits home. It connects the technical side back to the human side, the purpose. It's the ultimate so what for the software.
Exactly. Understanding the user and the business need is just as critical as writing flawless code.
Okay, those 7 principles provide a really strong foundation. Now, how do teams actually put this into practice in an organized way? You mentioned a life cycle.
Yes, the software testing lifecycle, or STLC, is basically a structured, planned sequence of activities to carry out testing efficiently and effectively. It generally comprises 6 key phases.
6 phases. Okay, what are they?
First, requirement analysis. This is where the QA team digs into the requirements, functional, non-functional business, to figure out what actually needs to be tested, what's testable.
Understanding the scope.
Got it. Second, test planning. This is the strategy phase. How are we going to test? What resources do we need? People, tools, environments? What's the schedule? What are the risks? This all goes into the test plan document.
The blueprint, like you said.
Exactly. Third, test case development. Here, the team actually writes the specific test cases and test scripts based on the plan and requirements. What are the steps, the data, the expected results?
Creating the actual tests.
Fourth, environment setup. You need the right stage to perform the play, right? This involves setting up the necessary hardware, software, network configurations, test data, creating the environment where testing will actually happen.
Getting the stage ready. Makes sense.
Fifth, test execution. This is showtime. The testers run the prepared test cases in the prepared environment, log the results pass, fail, and report any defects they find.
Running the tests, finding the bugs.
And finally, sixth, test cycle closure. This involves wrapping things up, evaluating if you've met the exit criteria defined in the test plan, creating summary reports, analyzing the testing process itself for lessons learned, and formally closing the testing phase.
Okay, that provides a clear structure. You emphasize the test plan in phase 2. Can you dive a bit deeper into why that document is so critical?
Absolutely. The test plan is, think of it as the master guidebook for the entire testing effort for a project or release. It's not just a nice to have, it's essential.
Why so essential? Can't experienced teams just figure it out as they go, adapt?
Well, you can try, but it's incredibly risky and inefficient. A good test plan provides that essential framework. It helps manage and control risk by explicitly stating what's in scope and, just as importantly, what's out of scope.
Preventing wasted effort on things that don't matter.
Exactly. It prevents scope creep in testing. It also helps you estimate the time, effort, and resources needed much more accurately. It clearly defines roles and responsibilities, who owns what part of the testing. It provides a schedule so everyone knows the deadlines. And crucially, it serves as a communication tool and a record. Remember that example of the company avoiding a lawsuit because their test plan documented that they weren't asked to test a specific compatibility?
Right, the ABC company. That's a powerful, real-world benefit.
Absolutely. It provides traceability and accountability. It's also a baseline for measuring progress and, later, for process improvement.
So what goes into creating a solid test plan? What are the key steps?
Typically, you'd start by thoroughly analyzing the product, its requirements, and the risks. Then you develop the overall test strategy, what approaches, what levels of testing. You define clear, measurable objectives and the precise scope. Then comes resource planning people, hardware, software tools. You develop a detailed schedule with milestones and estimations. And you define all the test deliverables, the documents, the reports, the metrics you'll produce.
Okay. And what key parameters would you always expect to see defined in the plan itself?
You definitely see the scope, what's tested, what's not. Objectives. Clear exit criteria. It is testing considered done. Maybe suspension criteria. When do we pause testing if things are too broken? Also, test deliverables, environmental needs, roles and responsibilities, staffing and training needs, the schedule, identified risks and mitigation plans, and importantly, the approval process, who signs off on this plan.
Wow, that's comprehensive. It really forces you to think through the entire effort up front.
It does, and it's usually a living document. It gets updated as requirements or risks change during the project.
Okay, that makes perfect sense. So we have the principles, the life cycle, the plan. Now let's broaden out again. You mentioned testing isn't monolithic. What are the main types of testing?
Right. We generally categorize testing into 2 broad buckets: functional testing and non-functional testing.
Functional and non-functional. Okay, let's start with functional. What's that about?
Functional testing is all about verifying that the software's features and functions behave exactly as they're supposed to, based on the requirements. It checks the what does the login function work? Can you add an item to the cart? Does the calculation give the right result? It focuses on specific actions and outputs.
Okay. And what are the different kinds of functional testing?
There are several key types. First, at the lowest level, we have unit testing.
Unit testing. That sounds small scale.
It's micro level. You're testing individual isolated pieces of code, a single function, a method, maybe a class, to make sure that specific unit works correctly on its own. Developers often write these tests themselves as they code.
Why test such small pieces? Why not just test the whole thing?
Great question. The benefits are huge. It increases confidence dramatically when you change code later if the unit tests pass. You know you haven't broken that specific piece. It encourages writing more modular, reusable code. It speeds up development overall because bugs are caught immediately, right where they were introduced. Debugging becomes way easier. And the cost of fixing those bugs is minimal because they haven't spread or been integrated yet.
Like testing each brick is sound before building the wall. Makes sense. How small is a unit?
It varies. But yeah, it could be a single line of code, often a method or function, sometimes a whole class. The key is that it's tested in isolation. For instance, if you have a function that adds 2 numbers and another that multiplies, unit testing checks each one separately. Does add 2 return 4, does multiply 3 return 9.
Got it. Building quality from the ground up.
Yeah.
What comes after unit testing?
Next up is integration testing. Once you know the individual units work, you need to check if they work together.
Connecting the bricks.
Exactly. Integration testing focuses on the interfaces and interactions between different modules or components. For example, does the login module correctly pass information to the user profile module? Does the shopping cart module interact correctly with the inventory system?
What are the challenges there? What if one part isn't ready yet?
That's a common problem. You often solve it using stubs and drivers. A stub is like a placeholder for a lower-level module that isn't finished. It just returns a fixed response. A driver is a placeholder for a higher-level module that calls the one you're testing. They let you test integrations even when the whole system isn't complete.
Clever workarounds. Okay, so units work. They work together. What's next?
Then comes system testing. Now you're testing the entire integrated system as a whole.
The whole wall, not just the bricks or sections.
Exactly. The goal here is to evaluate the system's compliance with the specified requirements from end to end. Does the complete application behave as expected? Think about that ballpoint pen analogy again. Unit testing checks the cap, the body, the ink. Integration testing might check if the ink cartridge fits in the body correctly. System testing is checking if the fully assembled pen actually writes smoothly and doesn't leak.
Great analogy. Okay, system testing checks the whole thing works technically. What about the users?
That leads us to acceptance testing, often called user acceptance testing or UAT. This is usually done towards the end. Its main purpose is to determine if the software is acceptable to the end users and if it meets the actual business needs in a real-world scenario. Is it ready for release?
So this is where the actual users or client representatives get involved.
Often, yes. There are different forms, like alpha testing, done internally by specialized testers, maybe in a lab environment, and beta testing, done by actual end users out in their own environment before the final release. It's the final check before going live.
Okay, that makes sense. Now, I've heard regression testing mentioned a lot. You touched on it with the car AC example. Why is it so critical?
Oh, regression testing is absolutely vital, especially in today's world of frequent updates and changes. It's all about ensuring that new code changes like bug fixes or new features haven't accidentally broken anything that was working perfectly fine before.
The fix one thing, break another problem.
Exactly. Like fixing the car's AC but breaking the gas sensor. Or that Vane Industries example. They fixed an invoice bug, but the fix broke the critical month-end profit report because they didn't test the impact on existing functionality with real data volumes. Regression bugs are common and can be really damaging.
So regression testing is basically rerunning old tests to make sure nothing got worse.
Essentially, yes. You re-execute previously run test cases to verify that the unchanged parts of the software still work correctly after a change has been made.
When do you typically do it? After every single change?
Ideally, yes, or very frequently. Definitely, whenever new features are added, bugs are fixed, performance issues are addressed, or even when just environment changes or patch fixes are applied.
It sounds like it could involve rerunning a lot of tests.
It can, which is why automation is so crucial for regression testing. But the benefits are huge. It catches unintended side effects early, reduces the cost significantly compared to finding these bugs in production, improves overall quality and user trust, and prevents those embarrassing old bugs from reappearing.
Can you be selective? Or do you always have to rerun everything?
You can be selective. There are different strategies. Unit regression, focused on the changed unit. Progressive, testing impact on related areas. Selective, choosing a subset based on risk. Retest all, rerunning the entire suite. Complete includes boundary testing or hybrid approaches. Often you prioritize based on the areas most likely affected by the change.
Got it. So it's a safety net. What about sanity testing? How does that differ?
Sanity testing is a very quick surface-level check. It's usually performed on a build that's considered relatively stable, perhaps after a bug fix or a minor change. The goal is just to quickly verify that the new functionality works roughly as expected and, critically, that it hasn't broken any major existing core functionality, like a quick health check.
So it's narrow and shallow.
Exactly. It's usually unscripted, very fast, and acts like a gatekeeper. If the sanity test fails, the build might be rejected immediately, saving the effort of more rigorous, time-consuming testing.
Okay. And how is that different from smoke testing? They sound kind of similar.
They are similar in being quick checks, but the timing and purpose differ slightly. Smoke testing is typically done on initial builds, like the very first time components are integrated or the first build of the day. Its purpose is to determine if the most critical core functionalities of the application are working at a basic level. Is the build even stable enough to start more detailed testing?
So smoke testing is like asking, does it even turn on? Does the main screen load on a brand new build?
Pretty much. It's often called build verification testing, BVT, or build acceptance testing, BAT. It provides very rapid feedback, often within minutes. If the smoke test fails, the build is likely fundamentally broken, and there's no point wasting time on further testing until the core issues are fixed. It minimizes integration risk early on.
So smoke test, is this initial build testable at all? Sanity test, did this recent change on a stable build break anything obvious?
That's a great way to summarize the key difference. Quick checks, different checkpoints.
Okay. One more functional type you mentioned, API testing. You gave the waiter analogy. Why is this becoming so important?
Right, API testing. APIs, application programming interfaces, are those messengers working behind the scenes, allowing different software systems to talk to each other. Think about booking a flight online. The travel site uses APIs to talk to airline systems, hotel systems, etc.
So they're like the glue holding modern software together.
Very much so. And testing them directly rather than just testing the user interface, UI that sits on top, has huge advantages. Well, it allows for much more effortless integration testing. It's crucial for mobile apps that rely heavily on APIs to get data. It offers more flexibility because APIs change less frequently than UIs. And crucially, finding bugs at the API layer is often much cheaper and faster than finding them through the UI later on. It lets you test the core business logic directly, leading to faster feedback loops and quicker releases.
So you're testing the engine directly, not just looking at the dashboard lights.
Perfect analogy. You're testing the core functionality, reliability under load, security aspects, all at that deeper layer.
Wow, okay. The world of functional testing is incredibly diverse. Now, what about the other big category, non-functional testing?
Right. If functional testing checks what the system does, non-functional testing checks how well it does it. It measures the quality attributes, the characteristics of the software.
Like performance.
Exactly. Performance is a major one. Performance testing aims to ensure the application performs well under its expected workload. How fast is it? How responsive?
Speed matters.
Absolutely. Performance testing also looks at scalability. How well does it handle an increasing number of users or data? And stability, does it stay reliable under sustained load or stress?
What kinds of performance tests are there?
Common types include load testing, simulating expected user load, stress testing, pushing it beyond normal limits to find the breaking point, endurance testing, checking for issues under sustained load over time like memory leaks, spike testing, sudden bursts of users, volume testing, handling large amounts of data, and scalability testing, determining how to scale up.
And if you don't do this thoroughly, what happens in the real world?
Oh, the consequences can be severe. Slow websites lead to frustrated users who just leave. E-commerce sites crashing during peak sales periods like Black Friday means huge revenue loss. Systems becoming unstable under load can lead to data corruption or complete outages.
So non-functional testing, like performance, is critical for user satisfaction and business success.
Absolutely. Other non-functional aspects include security testing, usability testing, reliability testing, compatibility testing.
Right.
It's a broad area focused on the overall quality and user experience beyond just the core features.
Okay, this is a massive amount of testing. How on earth do teams manage to do all of this efficiently, especially the repetitive parts like regression testing?
That's where test automation comes into its own. It's the key.
Define that for us.
Automation testing is basically the practice of using specialized software tools and scripts to execute test cases automatically, rather than having a human manually perform the steps.
So robots doing the testing.
In a sense, yes. Software robots executing pre-programmed instructions and comparing the actual results against the expected results. It's a huge game changer for speed, efficiency, and reliability, especially in fast-paced Agile and DevOps environments.
Okay, let's compare it directly with manual testing. You touched on this, but what are the main trade-offs? It feels like automation should always be the goal, but I guess it's not that simple.
You're absolutely right. It's not a silver bullet. There are trade-offs. Reliability. Automation is generally very high for repetitive, defined tasks. Computers don't get bored or make typos. Manual testing reliability can dip with repetition due to human factors like fatigue or oversight.
Okay, reliability leans towards automation for repetitive stuff. When should you use each?
Manual testing is still essential. It's ideal for things requiring human judgment and intuition. Exploratory testing, freestyle investigation, usability testing, how easy and intuitive is it for a human, ad hoc testing, unscripted, finding bugs serendipitously. Automation really shines for tasks that are repetitive, like regression tests, tests involving large volumes of data, testing across multiple platforms or browsers, and definitely performance and load testing where you need to simulate hundreds or thousands of users.
And the cost. Automation sounds expensive up front.
It is. Automation has a higher initial investment. You need the tools, you need skilled engineers to write and maintain the scripts. Manual testing has a lower barrier to entry initially, but the return on investment, ROI, for automation over the long term is usually much higher. Think about how many times you'll run those regression tests. Automating them saves countless hours of manual effort down the line. Manual ROI stays relatively flat or might even decrease if test suites grow large.
So invest early in automation for long-term savings and speed, but keep manual testing for the human-centric aspects.
That's the strategic balance, yes. And it's crucial to know when not to automate.
Oh, when shouldn't you automate?
Generally, don't bother automating tests you only run once. Tests that rely heavily on visual perception or subjective assessment are hard and often brittle to automate. Ad hoc and exploratory testing are inherently manual. And a big one, tests on highly unstable user interfaces. If the UI is changing constantly in early development, your automation scripts will constantly break and the maintenance effort will outweigh the benefits. Wait for some stability.
That's really practical advice. Don't automate just for the sake of it. Okay, what about the tools that make this happen? What are some popular ones?
There's a huge ecosystem of tools out there, both open source and commercial. For web application testing, Selenium is probably the most well-known open source standard. It supports lots of languages like Java, Python, C#, and works across different browsers.
Selenium? Right. Heard of that one.
For performance testing, especially for web apps and services, Apache JMeter is a very powerful and popular open source choice. It's Java-based, but has a user-friendly GUI. For unit testing in the Java world, JUnit and TestNG are the dominant frameworks. They provide the structure for writing and running those low-level tests.
Okay, web performance unit tests.
Yeah.
What else?
For mobile testing, Appium is a leading open source tool that works for both iOS and Android native, hybrid, and mobile web apps. And for API testing, Postman is incredibly popular for manual and automated API checks. Tools like Catalan Studio are also gaining traction because they offer a more integrated environment for web, API, and mobile testing, often with features aimed at being user-friendly, even for those less experienced with coding. And then you have commercial enterprise-level tools like HP UFT, formerly QTP, Ranorex, Tricentis Tosca, which often offer broader feature sets, integrated reporting, and vendor support, but come with licensing costs.
So lots of choices depending on your needs and budget. Now, you mentioned these tools operate within test automation frameworks. What exactly is a framework in this context?
Good question. A test automation framework isn't a tool itself, but rather a set of guidelines, rules, standards, and best practices for creating and managing your automation scripts. It provides structure. Think of it like the scaffolding around a building. It helps organize the work and make it more robust and maintainable. It might include things like shared function libraries, standard ways to handle test data, rules for object identification, and reporting mechanisms.
So it makes the automation effort more organized and less chaotic.
Exactly. It promotes consistency, reusability, maintainability, and scalability of your automation suite. There are different types like linear, simple record and playback, data-driven, separating test data from scripts, keyword-driven, using keywords to represent actions, modular, breaking tests into smaller modules, and hybrid frameworks that combine elements of others.
Okay, framework provides the structure. Now, this is where it gets really interesting for me, the practical application. How do teams actually write the tests that run in these frameworks? You mentioned scripts, cases, scenarios.
Right, clear documentation and definition are key here too. A test script is usually the most detailed. It's like a line-by-line instruction manual. Open browser, navigate to URL, enter username in field X, click button Y. Very specific steps with expected outcomes for each. Often, this is what the automation tool executes directly.
Very prescriptive.
Yes. A test case is a bit higher level. It describes a specific idea or objective to be tested, like verify that a user can successfully log in with valid credentials. It outlines the general steps, preconditions, and expected results, but might allow more flexibility in how exactly the tester or script achieves it. It focuses on the goal.
More about the what than the how.
Exactly. And then a test scenario is the broadest. It's a high-level description of an end-to-end functionality or user journey to be tested, like test the complete checkout process. It offers the most flexibility to the tester on how to approach it, maybe covering multiple related test cases within that scenario.
Okay, scenario case script, in terms of detail. What's the main purpose of writing these test cases?
The primary goals are always to ensure the features work as expected, according to requirements, to find defects early, to improve the overall quality and reliability of the product, and ultimately to reduce the costs associated with bugs escaping into production. They provide structured verification.
And tying this all together, how does this structured testing approach, especially with automation, help build truly robust software that, stands the test of time? What's maybe the biggest challenge in implementing this effectively in a real project?
The biggest challenge, honestly, is often setting up that robust automation framework correctly from the start. It requires a significant upfront investment in time, planning, and skilled resources. You need to make key decisions. Choose the right programming language for your scripts. Java is popular for its robustness, Python for its ease of use. Select a solid unit test framework like TestNG or JUnit that integrates well. Design the framework's architecture so it's scalable and maintainable as the application grows. Then you need to actually build reusable test modules. Decide on a clear reporting mechanism so people can understand the results, and crucially, integrate the whole thing with other tools in your development pipeline, like continuous integration, continuous delivery, CI/CD systems for automatic execution, and test management tools for tracking results.
It sounds like building a whole software project just for testing.
In many ways, it is. The purpose of all these steps is to create an automated testing system that isn't just a collection of scripts, but a reliable, scalable, maintainable, and efficient engine that truly supports the goal of delivering high-quality software rapidly. Getting that foundation right is key to long-term success.
So reflecting on all this, what does it all mean? We've taken quite a journey, haven't we? Through the core principles of testing, understanding the really vital role of the test automation engineer, peeking into all these methodologies and powerful tools, it's really clear that software testing is so much more than just finding bugs. It's about strategic thinking, it's about managing risk, ensuring quality, and ultimately it's about building trust. Trust in the digital products we rely on every single day.
Absolutely. And if we loop back to that final principle, the absence of error fallacy, it's the perfect reminder, even if you have the most technically perfect, bug-free piece of software, it ultimately fails if it doesn't actually solve a real problem for the user, if it doesn't meet their underlying needs. That human element, understanding the why, is just as crucial as the technical how.
That really resonates. And it makes me think, this raises an interesting question for you, our listener, listening in right now. How am I understanding these principles of testing, like early testing, context matters, absence of error? How might that change the way you approach any complex problem, not just in software, maybe in your own projects, your work, even everyday life? Perhaps it encourages looking for potential failure points earlier, testing assumptions before committing fully, or just always asking, does this solution really address the core need? Something to think about.
It's a mindset shift, really. Thinking critically about quality and purpose.
Keep exploring, keep questioning, and, keep trying to make things better. That's really what it's all about. And that's all for this deep dive.